So we have this situation. There's a hemispherical bowl kind of thing, an open hemisphere. Okay. It's rotating about this axis, which is its vertical symmetry axis. So it is rotating with a uniform angular speed omega. This surface has a coefficient of friction mu. So it's an So somewhere inside this, there is a particle which is lodged. Such that the position of the particle with respect to the center of curvature of the hemispherical surface is making an angle theta. So a particle P at theta equal to, let's say, 37 degrees as shown is at rest with respect to the rotating surface. So given that the radius of curvature of the hemispherical surface, this is, let's say, 5 meters, g is equal to 10 meters per second square, and the coefficient of friction is 0.2. Find omega if the friction acting on the particle is 0. There's no friction acting on it. Second, the range of omegas, so that the particle does not slip. So let's begin with this question. Just try this out. When you make the free body diagram, you see it is somewhat similar to what you've seen for banking angle of roads. Okay. So just begin by making the free body diagram for the given particle and see how that works out.
Sir, I cannot see your screen anymore.
You're not able to see the screen? Just a minute, I'll reshare it. Yeah, it's back online now. Okay, so in this case, since the particle is at rest with respect to the surface, it'll be easier if you make the free body diagram in the reference frame of the surface. So that becomes a rotating reference frame. So we'll have to take into account centrifugal force. So for the first part, how many forces will be acting on the particle?
3.
3 forces, right? Centrifugal, which will be radially outwards, normal reaction and weight. Okay. What will be the direction of centrifugal force here? I mean, it's of course radially outwards, but will it be a horizontal force? Will it be?
Sir, I don't understand.
So in the FBD, what is the direction of the centrifugal force?
Sir, radially outwards.
So radially outwards is what type of force? Is it like away from the center of curvature of the bowl, or is it like with respect to the vertical, how it's placed with respect to the vertical and horizontal? How is it placed? Centrifugal force.
Along the line of the radius.
Along the line of the radius, okay. But radius with respect to what? The radius of the circular motion, no?
Yes.
So that is the radius with respect to the axis.
Yes.
Understood, no? So does that make it a force which is like, if I name the center of curvature of the hemispherical surface, if I name this point O over here, and the particle is P, so this angle here is theta. Okay, so now where should I draw the centrifugal force vector? Should be along the line OP, or that is the
Sir, along
important.
OP, no?
No, see, that is the important thing to understand here. What is the axis of rotation? This vertical axis is the axis of rotation, no? So it will be radially outwards with respect
Along
to.
the radius.
So this will be the direction of centrifugal force. And this distance here, this is the perpendicular distance from the axis of rotation. So here small r will be capital R sine theta. First part, there's no friction. So a condition for equilibrium here without friction, that the centrifugal force is cos component balanced by mg sine component. So it will be close to some 1.5. One 1.6 almost actually. Yes, that's correct, Mansi. In terms of capital R, that will be okay. So that's the first part. Now in the second part, you have to find the range of omega. So that means now there's no constraint that there's zero friction acting. To find, so omega could be between some minimum value and maximum value. So both these limiting situations is where maximum friction is acting. In this case, the maximum friction acts down the surface because that mg sine theta component is dominating. And this is the case where maximum friction acts up the surface. Oh, sorry, it's the other way around.
Yes, sir.
This, yeah, is where it acts up. This case is where it acts. Has to go against gravity in the minimum case, and it has to go against centrifugal force. Okay, so this kind of situation. So you can refer to this FBD, but just you have to add friction to the analysis. Okay.
Written. Written.
Okay, so what you can understand here is that compared to this omega, if your omega is less, okay, then there's a tendency to slip downwards. Okay. So for range of omegas, if we take the first case that omega is less than square root of g by r tan theta, in that case, there's a tendency to slip down the surface. So because there's a tendency now to slip down the surface, so friction will act like this. So we have the equilibrium condition that mg sine theta is balanced by static friction plus, so the required static friction becomes this much. This condition is, and now this static friction cannot exceed mu n. So that means that the limiting condition here is that, so the smaller the value of omega you make, the more the demand on friction, but the demand on friction cannot exceed mu n, and n over here you can see is mg cos theta plus m omega square r sin theta. So this will give you a limiting condition on omega. Okay, so just take the terms of omega on one side and keep G on one side. So you have you can even write it like this by dividing the numerator and denominator by cos theta. Now see, for the other limiting value, we can use that little trick from Newton's laws, okay, or friction rather. This is the omega minimum we have got now. So from this we can see directly that the omega max will become this. Okay.
So 1.59.
So square root of that, no?
Yes, sir.
So this is about 1.26, I think. No? So this will show you that the range of omega in general should be in between these two values. And you can see the earlier one that we had calculated, which was for zero friction acting, is somewhere in between this. It was around 1.6, right? So have you understood how I got this value directly? Omega max directly from there? Just reverse the direction of friction. It's like the second case of that. So if we do this in detail, see here that now if we take a second case of this, if omega is greater than root g by r tan theta, then there's a tendency to slip up the inclined plane or up the surface. So now because there's a tendency to slip up the surface, okay, the direction of friction acting will have to support mg sine theta, be like this. So the equilibrium condition now will become that mg sine theta assisted by static friction is equal to m omega square r cos theta. Okay. And normal reaction is equal to mg cos theta plus centrifugal force is sine component. Okay. And again, friction should be less than equal to mu n. So when I now substitute these equations all here, it's the same set of equations as above, but direction of friction is reversed. So everywhere where we have friction, it should be replaced with a minus sign, minus of friction. So wherever we have mu finally, will get replaced from the above equations with a minus mu. So that is the trick over here. So according to this equation, the value of friction, the magnitude of friction required is this. And that should be less than equal to mu into mg cos theta plus m omega square r sine theta. Now, if you compare this particular equation that we have, this one, with the equivalent equation inequality that we had above, you'll see it's the same thing if we just replace the mu with the in the above one with a minus sign, because the left hand side has been reversed in direction. Okay, that's how we use the trick method. So if we keep omega square r on one side, here we have that's how ultimately this comes. You see, this final thing that we get is the same thing as just replacing the mu in the other limiting case. Just replace the mu with a minus mu. Okay. So replace mu with minus mu. So you reverse the direction of friction. So that's a little trick from friction, limiting friction type of questions. So you can avoid making that whole FBD and analyzing the whole thing again. Okay, so I'm just going to minimize this a little more, just go through cases again a little carefully. Understand the variations involving this situation where omega is less than this value. So there's a tendency to slip down the inclined plane versus the next one where omega is greater than this value. So there's a tendency to slip up the inclined plane. So friction is acting the opposite direction. And from that, how we get the range of omega. So I'll just scroll down to this free body diagram now. Okay, people. So hope this question is fully clear with this. So now we're done with these basics of circular motion. We'll come to another part of the application of mechanics in circular motion in general, which is the application of work by energy, and more specifically, conservation of mechanical energy in vertical circular motion case. So if you finished with this, let's move on to vertical circular motion. So if you refer to H.C. Verma, for example, vertical circular motion is not in the circular motion chapter. It is in the work by energy chapter towards the end of that chapter later. Okay. In Resnick Halliday, the applications for vertical circular motion are in between the work energy chapter again somewhere. Okay. So generally speaking, we have situations of vertical circular motion where we are able to apply conservation of mechanical energy. For example, so we'll look at situations where mechanical energy conservation can be applied. So one example of that could be something like this. This time we have an inverted hemispherical surface, and there's a fixed surface compared to the previous one where the surface itself was rotating. Here there's a fixed hemispherical surface, but it's smooth, and therefore when a particle is placed right at the top of it, it is in an unstable equilibrium position. Normal reaction is balancing weight, but it's in an unstable equilibrium position because the moment it is disturbed even slightly from its equilibrium position, it will tend to slide away from equilibrium. So particle placed over here, the smooth surface. So it's a hemispherical surface. Radius r. So now, given that the radius is supposed 10 meters and g is also 10 meters per second square, so a particle P is at rest initially. At the top. Now it is given a slight nudge. It's not given any kinetic energy, just a slight amount of motion with almost zero kinetic energy, but slight displacement from that equilibrium position. And starts sliding down the surface. So if you give it a slight nudge like this, it will start sliding down the surface like this. So find its speed as a function of its angular displacement. And from that, find the normal reaction acting on it. Again, as a function of angular displacement. So for this, given that its mass, let's say 2 kilograms, and take the value of G as, G I've already given earlier. Okay. And third, find the value of theta at which it slips off the surface. As you will understand intuitionally, it will not come to the bottom of the hemispherical surface. It will not reach this bottom position in contact. Somewhere in between, it will slip off the surface and go into a projectile motion instead. So we have to find the value of theta at which that happens. You can, and once you find the value of theta, you can also find the speed at that position. You can find the value of theta and the speed v. At the position where it slips off the surface. Okay, so since the surface is frictionless and normal contact force at any point always acts perpendicular to the direction of the instantaneous velocity, because the instantaneous velocity is tangential and the normal contact force will be normal or radial. So you'll see power delivered by normal reaction is 0. So work done by normal reaction is 0. So only the conservative force of gravity mg is doing work. So if you take the earth plus the particle as your system, your mechanical energy is conserved. That is the concept we'll apply here. So just take down the values of the question, then we will see how we can apply conservation of mechanical energy.
Sir, done.
Yeah, done with the question. Okay, so now what you do is make a free body diagram kind of thing when it is at an angular position theta, and compare that situation with the initial value where theta is 0 with the vertical.
I got the answers.
Yeah, so tell me the value of theta, or you can send it in the text message while others are working it out. You'll get it in either sine inverse, cos inverse, something like that. You can just send it that way only. Don't need to send it in degrees, just the inverse circular function is fine.
So the initial speed is 0. Oh, yes.
Yes, the initial speed you'll have to take as is just given a slight nudge, so its speed is tending to 0. So its speed as a function of theta will become like square root of 2gh, where h is the vertically downward displacement. So the first thing to understand here is that how we apply the conservation of mechanical energy principle. Yes, very good, Anirudh, that's correct. Okay, so if it's starting from here with initial speed almost tending to zero, okay, because you're giving it a slight nudge. Now, after some time, if it reaches somewhere here, let's say, it's reached an angular displacement of theta. So by now it has a linear speed v. So if you analyze the forces acting on the body, you can see that there's normal reaction and there's weight, only these two. Okay. So the important thing is that normal reaction acts radially outwards. So it is perpendicular to the instantaneous velocity at any instant. Therefore, work done by normal reaction is zero. So because work done by normal reaction is zero, so therefore we take the earth plus particle as a system, then work done by non-conservative forces is zero for the system. Work done by external forces is zero for the system. So change in kinetic energy plus change in gravitational potential energy is zero. Okay. So again, from this position to this position, if the vertical displacement is h, that in this diagram will be this displacement here. This is h, suppose. Okay, so we have the relation that plus half mv square minus mgh is equal to 3. And now from this triangle, you can see that, just draw this triangle separately. So this is our cos theta. This is h. You can see that h is equal to r minus r cos theta. So this becomes the answer to your first part. V as a function of theta. Now from the free body diagram, see the value of n. You have mg cos theta minus n. This is your centripetal force. So you plug in this value of v here. So that will give you n as a function of theta. Okay, so let's finish this up now. So we can see in general, this is your V as a function of theta here. I think we had taken R to be 10 meters, right? For this particular question, yes. So this will become square root of, 200. So that will be 10 square root of 2 into 1 minus cos theta in meters per second. Now for the second part, you can see that from here, the normal reaction is mg cos theta minus, so you can see this will become 2 mg into 1 minus cos theta, or take mg common, we have 3 cos theta minus you can see that therefore third part at cos theta equal to 2 by 3 or theta equal to cos inverse 2 by 3, the particle loses contact with a speed v of something like this. So you can use this problem actually as a simple template to solve virtually any type of vertical circular motion problem, but there are some standard cases of vertical circular motion we'll discuss next. Okay, so now let's look at the next template for vertical circular motion. So this is an even more standard kind of situation. So we have a particle tied with a string. So this here is a light but inextensible thread or string of length L. It is tied to P is a fixed point. Fixed peg on the wall. So now if we give the particle some initial impulse, such that it sets off with a velocity v0 at the lowest position, then from here, by the time the particle comes to some angular position, linear speed has changed to v. So you can see once again going from here to here, this vertical displacement being h, will apply conservation of energy. So tension is perpendicular to the instantaneous velocity at all points, because tension acts radially inwards and velocity is tangential to the circle. So work done by tension is equal to 0. So we have change in kinetic energy plus change in gravitational potential energy is 0. So this time going from this position to this position, you can see the change in kinetic energy is this much. The change in gravitational potential energy is so much. Okay, so now implementing this, we can once again see that here we get this kind of relation that v square is equal to v naught square minus 2gr into 1 minus cos theta. So you can see that as theta is increasing from 0 to 90 degrees, v is decreasing from v naught to square root of v naught square minus 2gr. We will talk about after 90 degrees later. Okay, now from that free body diagram, you can also see that tension is acting like this. Okay, now furthering the analysis here, you can see something interesting that from equation 1, see that if V naught is less than root 2 GR, then V becomes 0 at some value of theta less than 90 degrees. And at this position where P is equal to 0, tension becomes mg cos theta. That's what we're getting from equation 2. So in this case, so the system acts like a pendulum. So you think of this like so let's look at a numerical example of this case. So we have a thread of length 10 meters suspended from the fixed point P and a particle of mass 200 grams is given an initial velocity at this bottommost point of 10 meters per second. Take the value of acceleration due to gravity as 10 meters per second square. So first of all, find the maximum angular displacement from the starting point. Find tension in the thread initially So just try this out, people.
Sir, I sent you the answers.
Yes, very good, Apurv. Your answer is correct. Yes, Janvi, your answers are correct also. Okay, so straight away you can see one thing, that if you just check the numerical value of V naught here, you're given that the length of the string is 10 meters, so the radius of the circular motion is 10 meters. So root 2 GR is square root of 200. Okay. So if V naught is 10 meters per second, you can see that V naught is less than root 2 GR. So the particle will stop momentarily, that is, will not remain at rest, but only stop momentarily at some theta, which is going to be our theta max. Less than 90 degrees. So we can just analyze this simple situation like this, that so you can see that so this is the first thing that we get, that it goes to a maximum angular displacement from its initial thing. This much. Now you can also see that at this maximum angular displacement, yes, we'll come to all that. So now for the second part, you can see that the tension at various different points so when it sets off at theta equal to 0, the speed of V naught, what was the mass again? 200 grams. 4 newtons. This is the initial tension. So this initial tension will be the maximum. Whereas when it reaches the maximum angular displacement position, which I've taken as the last part of this, I'll do C and D also in between, B and C rather. Okay. But when it reaches this maximum angular displacement of 60 degrees, speed is 0. So at that moment, what is happening? The tension acting also one more important thing here. It will have B0, but it will have a tangential acceleration of G sine theta. Centripetal acceleration will be 0 because V is 0. It will have a tangential acceleration in this direction. So that's why it doesn't remain at rest. Okay, it has an acceleration, but it's momentarily at rest. This is a minimum tension throughout the motion. So as it sways as a pendulum, every time it goes through the vertical position, which is the mean position of the oscillation, it has maximum tension and maximum speed. Whereas every time it reaches the extreme position, it has minimum tension and speed equal to 0. So any other in between position you will see, like the 37, 53, etc. that we have talked about, the tension will be greater than 1 but less than 4, and speed will also be non-zero, though less than the initial speed of 10 meters per second. So use these FBDs as templates to complete this. Right. Yes, Dhruv, I will send the notes, etc. Okay, let's just wind up this question as we finish. So now you can see, for example, for the B part, when you reach the 37-degree position, first of all, you have to calculate what the speed is. That will come from work energy. Where H is again that this kind of term. So V becomes root 60 meter per second. So now tension, okay, will be such that 0.2. Weight is 2 newtons. So you can see how tension has reduced from the 4 Newton mark initially. This the minimum value it goes up to is 1 Newton later. But similarly for the C part, you can take theta as 53 degrees. So your V will become square root of 100 minus so H will become 4 meters. E will become root 20. Tension will become tension would have become 1.6 Newton. That. Okay, so we'll conclude today's session here. Next time we'll discuss what happens when V is greater than root 2 GR. So the string can go beyond the 90-degree position, and depending on how much speed it has initially, it can either complete the vertical circular motion or the string could become slack at some stage or lose its tension. So anyhow, that's it for today's session, people. Wish you all the best. I will send you the notes and the recording along with the previous one also. So
Thank you,
please,
sir.
yeah, start working on vertical circular motion questions also from HC Verma, but the work energy chapter, the last part of the work energy chapter will have vertical circular motion questions.
Okay, sir.
Okay, so that's it for today, people. Wish you all the best.
Thank you, sir.
So,
Yes,
so when will you come in Thane Center for doubts this week?
I'll probably be coming either on Thursday or Friday or maybe even on Wednesday. I will just send you the message on this thing
Okay, sir.
on the mentorship groups na for Thane. I will send the message. Okay.
Okay, sir.
You'll be
Sir?
coming
Thank you,
with-
sir. Bye, sir.
Yeah.
Sir, are you coming to Mira Road Center for doubts this week?
Yes, Nerul Center also I'll be coming. I think it will be on Saturday if I'm not mistaken. Let me
Sir,
just
not
check.
Nerul, Mira Road.
No, but Mira Road I will not be coming. Mira Road I think Hemant sir will be there for doubts or some other physics teacher will be there.
Okay, sir.